Students, I am Kalachelvi, Assistant Professor of Chemistry, JJ College of Arts and Science, Pudukkottai. Today, we have discussed about reduction and oxidation reactions. What is mean by reduction? Reduction, in simple words, can be explained as a given gain of electrons in an atom or the gain of hydrogen and the removal of oxygen is replaced by hydrogen. Then it can be explained as a reduction. So many more reduction reactions are available, but here we have discussed about the Clemmensen reduction. What is a Clemmensen reduction? The Clemmensen reduction is a reaction that is used to reduce aldehydes or ketones, that is a carbonyl compounds, or converted to alkanes using HCl and zinc amalgam. For example, acetophenone is converted to ethyl benzene. Benzaldehyde is converted to toluene. So these are some examples of Clemmensen reduction. So this reaction was reported by Clemmensen of Park Davies in 1913. It is the reduction of carbonyl groups, that is aldehyde or ketone, to converted to methylene group. This reaction done with the zinc amalgam and hydrochloric acid, and it is generally known as a Clemmensen reduction. The Clemmensen reduction is particularly effective at reducing aryl alkyl ketones such as those formed in a Friedel-Crafts acylation. So this is a general equation format for Clemmensen reduction. So here we have to take one ketone, that is carbonyl compound. That the carbonyl compound attached with the R1 and R2 group. R1 may be substituted any alkyl or aryl group. R2 may be substituted hydrogen or alkyl or aryl group. So these carbonyl compound, when treated with the zinc amalgam and HCl, it is converted to a alkane. So this is a general formation of Clemmensen reaction. And this one is a mechanism. So the carbanionic mechanism of reaction shows that the zinc attacks directly the protonated carbon, while the carbenoid mechanism is a radical process and reduces the happening of a zinc metal surface. The reduction takes place at the surface of the zinc catalyst. In this reaction, alcohols are not postulated as intermediates because subjection of the corresponding alcohols to these same reaction conditions does not lead to alkanes. So these are the applications of a Clemmensen reduction. So this reaction was widely used to convert a carbonyl group into a methylene group. Also important application in the preparation of polycyclic aromatics and aromatics containing unbranched hydrocarbon chains to reduce aliphatic and mixed aliphatic aromatic carbonyl compounds. So here we give another example. Heptanol is converted to heptane. Benzoyl cyclopropane is converted to allyl benzene. So these are some examples of Clemmensen reduction. Next, we go to Wolff-Kishner reduction. What is Wolff-Kishner reduction? The reaction in which aldehydes and ketones, that is carbonyl compounds, are converted into a alkane. So both Clemmensen and Wolff-Kishner, the carbonyl compounds are converted to alkanes, but the mediums are different. In Clemmensen reduction, we have to use zinc amalgam and HCl. So in Wolff-Kishner reduction, the reaction takes place in presence of hydrazine, base, and using thermal conditions. The Wolff-Kishner reduction was discovered independently by N. Kirchner in 1911 and L. Wolff in 1912. The Wolff-Kishner reduction is a reaction used in organic chemistry to convert carbonyl functionalities into methylene groups. The Wolff-Kishner reduction is an organic reaction used to convert an aldehyde or ketone to an alkane using hydrazine, base, and thermal conditions. Because the Wolff-Kishner reduction requires highly basic conditions, it is unsuitable for base-sensitive substrates. So this is a general formation of Wolff-Kishner reduction. The carbonyl compound, when treated with hydrazine and base and also thermal conditions, the liberation of N2 molecule, it gives a alkane. And this one is a mechanism. When aldehydes or ketones are treated with hydrazine, and potassium hydroxide in ethylene glycol. It's a result in the formation of alkanes. So the first step in this reaction in the formation of a hydrazone anion by deprotonation of the terminal nitrogen by alcohols. So here the ketone is converted to hydrazone. Hydrazone medium is converted to a alkanes. So this is a mechanism, and these are the applications of MPV reduction. Wolff-Kishner reduction. So this reaction has a very broad application in organic synthesis, especially for the multi-walled carbon nanotubes. In 2011, Peters and Green reduced a tricyclic carbonyl compound using Hong-Minlin modification of the Wolff-Kishner reduction. Several attempts towards decarbonylation of tricyclic allylic acetate containing ketone failed, and the acetate functionality had to be removed to allow successful Wolff-Kishner reduction. Finally, the allyl alcohol was installed via oxyl plumbation. The Wolff-Kishner reduction has also been used on kilogram scale for the synthesis of a functionalized imidazole substrate. Next, MPV reduction. What is MPV? Mervin-Bondorf-Verley reduction is also called MPV reduction. So the reduction of a carbonyl compounds to corresponding alcohols by using an aluminum alkoxide as a catalyst and isopropanol as a reducing agent or hydride source is known as MPV reduction. MPV reduction is a reduction of aldehydes and ketones to their corresponding alcohols utilizing aluminum oxide catalyst in the presence of sacrificial alcohol. MPV reduction was discovered by Mervin and Schmidt and separated by Wehrle in 1925. They found that the mixture of aluminum oxide and ethanol could reduce aldehyde to alcohols. Bondorf applied the reaction to ketones and upgraded the catalyst to aluminum isopropoxide in isopropanol. So this is a general formation. Conversion of aldehyde or ketone into corresponding alcohol by treatment with aluminum isopropoxide in isopropanol solution. So this reaction is reversible and is called open-R oxidation. So this is a general formation of MPV reduction. And this is a mechanism. The first step is the carbonyl oxygen is coordinated to active the tetra-coordinated aluminum intermediate. Between intermediates, the hydride is transferred to the carbonyl from the alkoxy ligand. At this point, the new carbonyl dissociates and gives the tri-coordinated aluminum species. Finally, an alcohol from solution displaces a newly reduced carbonyl to regenerate the catalyst. These are the applications of MPV reduction. This method of reduction is specific for carbonyl group and therefore it can be used for reducing aldehydes and ketones containing some other reducible group such as a double bond, a nitro or an ester group which are not reduced under these conditions. So this is a main example for MPV reduction. Crotonaldehyde is converted to crotyl alcohol. Next we discuss about open-R oxidation. What is oxidation? The loss of electrons from an atom, molecule or ion is known as oxidation. Oxidation can also be defined as the gain of oxygen and the loss of hydrogen. The increase in the oxidation state of atom, molecule or ion is known as oxidation. Here we discuss about open-R oxidation. Named after Rupert Victor open-R. It is a gentle method for selectively oxidizing secondary alcohols to ketones. The reaction is the opposite of Mervin-Bondorf-Verley reduction. The alcohol is oxidized with aluminum isopropoxide in excess ketone. This shifts the equilibrium toward the product side. So though primary alcohols can be oxidized under open-R oxidations, primary alcohols are seldom oxidized by this method due to the competing aldol condensation of aldehyde products. The open-hour oxidation is still used for oxidation of acid labile substrates. So this is a general formation of open-hour oxidation. So the open-hour oxidation is the process of conversion of a secondary alcohols to ketones by selectively oxidation. So this reaction takes place in the presence of aluminum triisopropoxide in excess of acetone. So this is a mechanism. In the first step, alcohol coordinates with aluminum isopropoxide to form a complex. This complex reacts with the ketone to form a 6-member transition complex. The alpha carbon of the alcohol is converted to the carbonyl carbon from the aluminum catalyzed hydride shift. The acetone proceeds over a 6-member transition state. The desired ketone is formed after the hydride transfer. So this is a mechanism. And these are the applications of open-hour oxidation. The open-hour oxidation is used to prepare analgesics in the pharmaceutical industry such as morphine and codeine. For instance, codeine is prepared by open-hour oxidation of codeine. Thank you.